In 1915, Karl Schwarzschild discovered a solution to Einstein's brand new equations of general relativity, a solution that we now understand describes a black hole. But before black holes were ever taken seriously, the Schwarzschild solution revealed the possibility of the wormhole. In 1916, Ludwig Flamm realized that in certain coordinate systems, the gravitational hole described by the Schwarzschild solution was not a dead end, rather it was a two-sided funnel, but leading where? As we saw in our recent episode, the Schwarzschild solution describes two symmetric regions of space-time, and the funnel itself is the wormhole connecting them. In 1935, Albert Einstein, along with Nathan Rosen, expanded on Flamm's idea, but not into a theory of wormholes, instead as a theory of particles. Einstein and Rosen imagined two regions described by the Schwarzschild solution not as parallel universes, but rather as overlapping layers of the same universe. It's easier to visualize in 2D, where each layer is a sheet. In this picture, the funnels connecting the layers would behave like particles that could move around and interact with each other. And if you thread the funnels with electromagnetic field lines, then they act like charged particles. Now, it turns out that this is almost certainly not what particles are, but the Einstein-Rosen paper inspired others to take the wormhole seriously, and inspired the name for these Schwarzschild wormholes, the Einstein-Rosen bridge. The wormhole lay mostly dormant for another 20 years before it was resurrected, this time not to build particles, but in an attempt to break causality. John Archibald Wheeler, along with his ex-student Bob Fuller, realized that Einstein and Rosen's bridge did not necessarily have to connect parallel layers of reality, it could instead connect distant regions of our universe. Fuller and Wheeler realized that such a multiply connected space-time could allow near instantaneous travel across the universe because the wormhole throat would remain the same very short length no matter how far apart its ends were. And they also realized that this would allow time travel. For example, if one end of the wormhole were accelerated into a circular path at near the speed of light, its clock would freeze compared to the other end. By entering the non-moving end of the wormhole, you would always travel backwards to the instant when the other end was first accelerated and frozen in time. Fuller and Wheeler knew that any traversable wormhole could violate causality. So to save causality, they delved deeper into the Schwarzschild wormhole than anyone had before. We are going to try to follow them. We've been showing this classic depiction of the wormhole described by the Schwarzschild solution. It represents the fabric of only two dimensions of space at a single instant in time. The technical name is an embedding diagram, a 2D spatial sheet sliced out of 4D space-time. Let's keep time frozen for the moment and add back in the third spatial dimension. The ring of the wormhole is actually a sphere the size of the Schwarzschild event horizon. If we could pass through that event horizon, we would not find ourselves in a black hole. We'd be instantly transported to the region beyond. But if we unfreeze the wormhole, if we add back the dimension of time, that journey becomes impossible. Fuller and Wheeler proved that the Schwarzschild wormhole collapses on itself so fast that nothing, not even light, can make it through. To see that, we need to turn back to a representation of the black hole that we saw in our parallel universe episode. This is the Kruskal-Zakeres diagram. Now, I don't want to go into the complexities of this right now, check out the previous episode for more details, but the TLDR is that moving up means moving into the future, and moving left means moving towards the black hole. But space and time coordinates are blended and mutated so that time doesn't freeze at the event horizon, which itself becomes this 45-degree path. Sub-light-speed paths are always at a steeper angle. The strange extra layer that Einstein and Rosen discovered is represented as a mirror reflection to our universe. The black hole also has a mirror reflection that we call the white hole. The black hole represented here is a so-called eternal black hole. No matter where you are in the universe, if you travel to the left at any possible speed, you'll find the event horizon and enter the interior of the black hole. But what if you could travel at impossible speeds? Then you could potentially reach this strange point, the nexus between the white and the black hole. The Kruskal-Szekeres diagram shows that faster than light travel is needed to cross the wormhole. But to really understand this, we need to see how the wormhole evolves. The embedding diagram we saw was a particular time slice of the Schwarzschild spacetime. If we instead take a slice a little further in the future, we see the wormhole throat has narrowed in width, and passing through means crossing two event horizons, and the region in between is the inside of a black hole. When that time slice hits the singularity, the wormhole has closed. If we include time slices in the past, we see the full evolution of the wormhole. It opens, it widens, it shrinks, and then pinches off again. The Schwarzschild solution really represents two things. It accurately describes a non-rotating black hole if you just consider its future state, where the wormhole is pinched off. But if you consider its entire timeline, it describes a wormhole that opens and then shuts again. Fuller and Wheeler showed that even at the speed of light, nothing can get through such a wormhole.
Einstein's field equations seem to be a good description of our universe, and different solutions to these equations describe different scenarios in our universe, or specifically how space-time behaves in our universe. For example, we can use the Minkowski metric to describe empty, flat space, and we've got the Schwarzschild metric to describe what happens around a stationary black hole, and we've got the Kerr metric as well to describe what happens around a rotating black hole. Finding solutions to the Einstein field equations is hard, but we have found some, and it seems like we've also observed the corresponding phenomena in outer space. Now, the Kerr metric can be analysed to describe the behaviour and properties of rotating black holes. The first interesting point is that for a rotating black hole, the event horizon is not the only boundary we need to be considering. Remember, the event horizon is the boundary beyond which even light cannot escape the black hole. This exists for a rotating black hole, but it's not spherical like we believe it is for a stationary black hole. If our black hole is rotating about this axis, let's say this is the z-axis, then the event horizon looks more like a squished sphere. Squished at the poles specifically, and it extends further out at the equator. So the shape looks a little bit different. Interesting. But as we mentioned earlier, this is not the only boundary we need to be studying. Firstly, the event horizon that we've just discussed comes out naturally from the Kerr metric's mathematics, but it's known as the outer horizon, which might suggest to us that there must be an inner horizon. Now, this inner horizon is basically just an artifact of the mathematics of the Kerr metric. It's not necessarily physical. It doesn't necessarily exist in the real world. And I'm being a bit weird about this, and there's a particular reason for that. In fact, there's a couple of reasons for that. Firstly, remember that the Kerr metric is meant to describe the empty space around a rotating black hole. It's not necessary that it describes the inside of a black hole perfectly, but we can extend the maths to inside the black hole, and this is what the Kerr metric gives us, the existence of an inner horizon. Secondly, as far as we know, there's actually no way for us to find out what happens inside this black hole, because not even light can escape the outer horizon. And for these reasons, we're not going to go too deeply into the details about the inner horizon, but it does exist, seemingly in the mathematics at least, and I'd recommend looking it up if you want to learn more. But we're not done there for the surfaces of a rotating black hole. Another surface worth mentioning is known as the outer stationary limit surface. Beyond this boundary, an effect known as frame dragging occurs. Now, to understand this, let's imagine that we're looking down at our black hole. Basically, we're looking at it from the North Pole, and let's say that the black hole is rotating this way, anti-clockwise. Oh, and North Pole is kind of just what we call a particular pole. It's kind of convention, so don't worry too much about which pole is which. Any particle or object inside this stationary limit surface must rotate with the same sense as the black hole. Even photons, the objects that move at the speed of light, the cosmic speed limit, if you will, cannot move in this direction. They cannot move against the rotation of the black hole. In fact, at the stationary limit surface, photons trying to move in this direction will move with the black hole, but photons trying to move in the opposite direction just sort of remain stationary. Again, a rather hand-wavy description. Basically, the angular coordinate of this photon remains the same. And inside this stationary limit surface, everything has to be moving with the rotation of the black hole. Let's imagine that we've got a photon, currently outside our stationary limit surface, and it's moving with some angular momentum, basically against the rotation of the black hole. As it gets closer and closer to the black hole, this is what it has to do. As you can see, as it crosses the stationary limit surface, it moves with the rotation of the black hole. And if a photon has to move with the rotation of the black hole, then any other object which has mass and inevitably moves slower than a photon must do so as well. This is what we mean by frame dragging. If we are to find a particular reference frame, like a point of view of looking at this particle inside the stationary limit surface, then in order for us to see the particle as stationary, our reference frame needs to be moving with the rotation of the black hole. The black hole's rotation is dragging our frame. This frame dragging effect is literally caused by the warping and bending of space-time around the black hole because it's rotating. As a black hole rotates faster and faster, the event horizon and the stationary limit surface separate out so we can actually see a region between them. This brings us onto another interesting point. Because the event horizon is not the same as the stationary limit surface, there's a region between the two, known as the ergosphere, in which particles are forced to rotate with the same sense as the black hole, but crucially, they can get away from the black hole. They haven't fallen into the event horizon yet, and so we can actually receive particles that have been in the ergosphere. As a result of this, energy, technically work, can potentially be extracted from a black hole. This is why the region is called the ergosphere. This possible extraction of work is rather complicated, is described by the Penrose process, which deserves a video of its own. Basically, the particles are carrying energy away from the black hole. Interesting, right? Another interesting feature of the Kerr metric is its description of the singularity at the center of the black hole. First of all, some of you might be familiar with the idea that at the center of a black hole, there's a region of what we suspect is infinite density. Basically, mass is packed so tightly into such a small space that the density, basically mass divided by volume, is infinite. At these singularities, our mathematics breaks and our minds blow up. But luckily we don't know yet what happens at the center of a black hole because we don't have any way of getting information from the center of the black hole. Still, it's worth thinking about. And interestingly, for a stationary black hole, the singularity is thought to be a very tiny infinitesimal point. Whereas the Kerr metric actually tells us that for a rotating black hole, the singularity is not a point, but rather a ring. A very thin, very narrow ring around the rotation axis.
Black holes are some of the simplest objects in the universe. By that, I just mean that they are characterized by only two attributes, mass and spin. Okay, there's also charge, but since black holes should essentially be neutral, mass and spin are the two that count. Mass is relatively easy to determine. Far away from a black hole, you can even use Newtonian physics. By measuring the gravitational effects of the black hole on other bodies, you can estimate the mass of the black hole. This has been done, and black holes have been found with masses ranging from just a few times our sun, stellar mass black holes, up to billions of solar masses, supermassive black holes. It's generally accepted that there is a supermassive black hole at the centers of most galaxies, including our own. But what about spin? Since black holes form from collapsing stars and all known stars rotate, all black holes should also be rotating. I mean, what are the chances that a bunch of matter just collapses into a point perfectly with no rotation? It's just not going to happen. And then additional matter falling into the black hole contributes its angular momentum. So like a figure skater pulling their arms into a point object, you can imagine black holes get spinning pretty fast. But spin is harder to measure because, unlike mass, it only affects objects relatively close to the black hole. But there is a way to do it. Actually, 3 ways. To understand all of them, you have to understand ISCO. In Newtonian physics, around a compact mass, you can place an object in a circular orbit at any radius, and it will be stable. It doesn't matter how close you get. This is not the case according to general relativity. Here, there is an innermost stable circular orbit, with a radius known as r ISCO. Closer than this, and no orbits are stable, they all fall into the black hole. So when you're looking at a black hole that is feeding, the innermost edge of the accretion disk is at r ISCO. What's useful for our purposes is that our ISCO depends on the spin of the black hole. The faster it's spinning, the smaller our ISCO becomes, assuming it's spinning in the same direction as the matter in the accretion disk. The rotation enables particles to orbit closer to the black hole than they'd be able to for a non-spinning black hole. So you can kind of think of it as though the spin is supporting the particles against the relentless pull of gravity. Now, spin is normally discussed in terms of a dimensionless parameter that ranges from 0, no spin, to 1, maximum spin. Though I guess you could also have spins down to -1 if the black hole is spinning in the opposite direction from the accretion disk. Now, as spin increases, our ISCO decreases by a factor of 6, shrinking down to the size of the event horizon. And this sets what many scientists think is the maximum spin a black hole can have.
Nobody has seen a wormhole, nobody has produced one, nobody knows if it is just some beautiful math, but without a physical reality.
Well, we'll take the world's best quantum computer and see if we can map that into building a wormhole.
And then it became just at the edge of what's possible.
I think the discovery of the Higgs, which came about 10 years ago, was up to that point the most exciting point of my entire career. This, to me, is equally exciting.
It can begin to explore quantum states that are very hard to realize in nature directly.
Now the wormhole becomes traversable. It opens. You really can go through. So the story begins in 1935 when Einstein wrote a paper with Rosen where the first time Einstein-Rosen bridges appear. And these are bridges that connect two seemingly unconnectable pieces of space-time.
ER, Einstein and Rosen, they pointed out that solutions to general relativity allowed for two black holes, which are connected, but with a kind of bridge, what we call a wormhole. But that wormhole has the property of being non-traversable.
Wormhole is a very unstable passage. It opens and it closes and it gets chaotic and it gets destroyed very fast.
So Einstein, when he proposed the wormhole, he was very frustrated because you couldn't actually go through a wormhole, and he was able to realize that himself. And so what good is a wormhole if you can't put anything through it? And it turns out that that's because he wasn't putting in the quantum physics.
1935, same year, another paper, the EPR paper, which is Einstein, Rosen, Podolsky.
EPR is about quantum entanglement and what Einstein called spooky action at a distance, something he was not happy with.
Entanglement is this property that subatomic particles, they are partners. Even if you take them apart and take them at the other edge of the universe, they hold information that if you measure the one, you know what the other will be. So entanglement is a strong correlation.
Einstein didn't like quantum mechanics, and this made it very challenging for him to understand how to reconcile quantum physics and gravitational physics. Physicists want to understand as much as they can about how the universe works, so it has been a challenge which has occupied many scientists over decades to understand better how quantum physics and general relativity fit together into a coherent picture.
Einstein's dream was to figure out how to connect them.
Those two papers, there was no reason to think at the time or for decades afterward that they had anything to do with one another apart from there being some authors in common.
And then comes 2013, Maldacena and Lenny Susskind. They say ER equals EPR. They are the same. This is very daring.
wormholes and entanglement are the same thing. That was totally unexpected. One of them has to do with general relativity. One of them has to do with quantum mechanics. Didn't seem like they had anything to do with each other.
A lot of times in physics, you can have two different descriptions of the same thing, but it's just sort of a remapping of the same physics. And we call that a duality.
The basic idea was that when you have quantum entanglement between two black holes, necessarily there will be a wormhole connecting them.
It's like saying gravity equals quantum mechanics, if we want to say it in a simplified way. So there we have a picture of quantum gravity.
We have this dictionary that relates gravitational phenomena to ordinary quantum physics.
You can tackle the same physics from these two different angles, and that's the most concrete paths forward we have in building a full theory of quantum gravity.
The physics of the black holes, we think is physics of quantum gravity, but we cannot send an experiment in a black hole and validate that.
So instead, we can ask, can there be quantum systems whose dual description looks like wormholes? I think it might have actually been during a talk by Juan Malmacena about dr equals EPR that I started to wonder to myself, could traversable wormholes exist, right? And people thought it was fascinating as an exotic configuration of space-time, but I think many people probably suspected that it couldn't work. So we saw that it could.
One of the magical things about quantum mechanics is you can actually have negative energy, and this allows you to do things that you would have thought otherwise were impossible.
What Daniel Jaffrus showed was that if you introduce what's known as a negative energy shock wave, you can support your wormhole and get something from one end and have it come out the other.
Now I'm an experimentalist, so I look at that and I do. All right, what can I do about that?
We were thinking, we have the ability to do things in quantum in the laboratory. We're physicists. So could we imagine actually doing something with wormholes? It almost occurred to us immediately that we should be using the best quantum system that we know how to manipulate. And what is that? It's a quantum computer.
Quantum computers speak a different language than the ordinary language of bits. A bit, you look at it, okay, it's a 0 or 1, that's it. The correlations among qubits are richer and a lot more interesting than correlations among bits. It's this language of quantum entanglement. And so there's a world out there, this extravagant quantum world, which we just haven't been able to explore.
I've worked on a few projects at Google Quantum and got to know the device a bit. And the Google device is the best quantum computer that is around. All the magic happens in this little chip. You have the actual qubits as these superconducting pieces of aluminum, and that's where the entanglement happens. We had the access to the Google quantum computer. I came over with Maria and Daniel and Joe, and we were like, we have a proposal to try to, observe a wormhole on the quantum computer.
And to put the proposal together, it was obvious that these are the people.
In physics, you have to have the courage of your own convictions, and you say, well, maybe it won't work the way that I thought, but we'll learn something by trying. And that's really the attitude we had going into this. I don't think we really thought it was going to work, but we thought we would learn a lot by seeing how far you could get.
They didn't say, you're crazy, let's do something else. They said, okay, you're crazy, let's do it.
You can use the holographic duality to create the quantum version of the system. We look instead at this set of entangled qubits, and we evolve it in a way that has exactly the same physics as the gravitational wormhole. And so on the quantum computer, we can directly send a qubit from one side of the wormhole and watch it come out the other. If you take the physical system that theoretical physicists say, this is a wormhole, and you work out pencil and paper, so how good of a quantum computer do I need? You get an answer that's like a quantum computer 10 years from now. It looks hopeless.
But we thought, let's try.
All right.
So we are here in our GQ2 lab, and then the controlled signals actually are produced in these racks sitting next to the cryostat.
When you try to just run a wormhole as the theorists have prepared it on a quantum computer, you find that you need to implement this very large system.
So that's big. That's a big, fat problem. I cannot put it on an experiment.
And so what we have to do is we have to do what physicists call coarse graining. So you want to preserve certain features, in this case gravitational features, while throwing away all the unnecessary components. We knew we needed to go to a smaller system size, and so we were kind of banging our head against it for a year or something. And then finally you come up with a weird idea that might work. The idea of rewriting it as a neural network is something that's kind of out there, and that's like, it's a weird idea because you usually don't think of physical wormholes as neural networks. The wormhole itself that has like these many parameters that we treat as neural network weights. We then have a data set that we're going to train on, which is the dynamics that we want to observe that correspond to a wormhole. So it sounds like a generic machine learning problem now, and we can just like plug it straight into the machine learning toolbox. I proposed the idea and tried it out. The original system has 210 terms. The machine learning managed to keep all this intact while making a much smaller system.
It's still baby enough that it fits on the crib.
That was the kind of first moment where like, it might be possible, you know? this whole wormhole thing we've been talking about for 2 years, like maybe we can actually do it. At probably like 2 in the morning, I was running these quantum circuits. We're looking for a peak. That's the qubit making it through the wormhole. I'm watching the data as it comes out. There's a little bit of a noisy peak. At first, I was like, this is probably just noise artifact. But as the data kept coming and the peak kept getting clearer, it was like, this is a wormhole. I think I just saw one. And so I was immediately like sending it off to Maria and the others. Like, I think we have a wormhole, guys.
He said, it's there. I said, no kidding, he's there. It was nuts. It was nuts.
What happens is
The qubits of the Google quantum computer are making a little bit of extra space, and that's our wormhole.
a pulse of negative energy falls into the wormhole.
Now the wormhole becomes traversable. It opens.
You put a qubit through one side of the wormhole.
The qubit is now in the interior of this wormhole.
That information will actually spread over the entire quantum system. This spread of quantum information,
It becomes shared by many particles in the form of quantum entanglement. And then, rather remarkably,
it has to refocus as a single qubit. And then, as the wormhole is closing, the qubit is exiting.
I was absolutely astounded. I thought we would get maybe a few steps towards a real wormhole and a real quantum computer. And I never really believed that we'd get all the way to something that was real.
The experimentalists have like reactions that they want to hug the machine.
I told my brother in Greece on the phone, and he squealed, and he said, "Are you destroying the world? What are you doing?" And it was difficult to explain to him that nobody is in danger from this wormhole. On the processor, if we had a quantum-sensitive eye and looked in there, we wouldn't see a ripple of space-time. We would see the physics that we expect from the gravity point of view and from the quantum point of view. So if that is the case, then we're making contact between quantum and gravity.
That's been the holy grail of my whole career, is to understand quantum gravity and the things that go with it, like wormholes. We are studying quantum gravity literally from the ground up.
Einstein committed his life to arrive to some understanding of quantum gravity. Here we are, almost a century later. I wish he was alive to see this, because I would like to know what he would say.
Well, what Einstein has said, he would have said ER equals EPR. I told you, I knew that in 1935. But he didn't.
I think this is concrete experimental evidence for ER equals EPR.
The vector is pointing right from the experimental point of view.
This is a confirmation, a direct exploration of this connection between quantum entanglement on the one hand and the way space is knit together and holds itself together.
As Google builds more and more capable quantum computers, we will eventually be able to get this into a regime where we don't even know how to predict what's going to happen. And I think we're going to have hundreds of my fellow physicists now writing papers about all the other things you can think about doing now that we've sort of got this door a little bit open.
And as always in physics, when you are able to explore a new frontier, there will be discoveries that weren't anticipated. Just like when you build a more powerful accelerator to study particle collisions or a more powerful telescope to look at the more distant universe, a more powerful quantum computer will be able to study highly entangled matter that we've never been able to look at before.
I think in the next 20 years, there are going to be a lot of fun for fundamental physics. Being very close with quantum, we're going to learn a lot.
There's so many questions that one could explore using these ideas. And I think most exciting are the questions that we can't yet pose.
According to general relativity, when anything with mass or energy is introduced into a wormhole, its gravitational effect immediately closes it. In other words, in order to keep the wormhole open and traversable, some form of negative energy or negative mass is needed to provide a kind of force against the gravitational collapse of the wormhole to keep it open. Negative energy or mass is something not considered physically possible. But this is not the case in our quantum system. Negative energy can be simulated in the system by manipulating the electrical field to change the spin direction of the qubits. So approximately, a propagating electrical field could keep the quantum wormhole open, simulating the effect of negative mass in space that would be required to keep a real wormhole open. Okay, so now, all the team needed was a way to set up and manipulate entangled particles. This is where Google comes in. Their Sycamore quantum computer can do precisely that type of thing. The researchers created an entangled state between two sides of a quantum system using 7 qubits. A qubit is a basic unit of information in quantum computers, just like a bit is a unit of information in a classical computer. The difference is that unlike a classical bit, which consists of a 1 or 0, on or off, a qubit can consist of any state between a 1 and 0. It's a superposition of the two. The 7 qubits simulated a wormhole consisting of 7 pairs of particles. One set of particles acted as the entrance of the wormhole, and the other entangled set acted as the exit of the wormhole. 2 more maximally entangled qubits were used in this experiment, bringing the total to 9. One of these qubits is called a probe, and the other is called a reference.
the probe was swapped out with a particle located at the entrance of the wormhole. That probe's possible states then quickly got entangled with the states of the other particles at the entrance, spreading or scattering this information among them, kind of like a drop of ink in water. This is roughly analogous to a particle entering the mouth of a wormhole. Next, the experimenters simulated the pulse of negative energy needed to keep the wormhole open so that the information or particle could be pushed through it. They did this by rotating the spin direction of the qubits by changing the electric field. As the wormhole continued to evolve, the scrambled information from the probe was transferred to the exit of the wormhole, consisting of the 7 particles on the other side. And then it unscrambled and focused on a single particle at the exit of the wormhole. This is analogous to the scrambled drop of ink in water turning back into a drop. The researchers confirmed that information was transferred from the probe qubit at the entrance to a particle at the exit by measuring the amount of entanglement between the reference qubit and the particle at the exit. So this confirmed that information had indeed been transferred via a mechanism which is similar to the physics of a traversable wormhole. The surprise is not that the message made it across in some form, but that it made it across unscrambled. In the ink analogy, the drop of ink was scattered, but then was unscattered. This suggests that the physics of a traversable wormhole was simulated. The researchers said that in principle, if they had 2 quantum computers on opposite sides of Earth, a refined version of this experiment should be able to transmit quantum information from one side to the other. So, if this is shown to be correct, that could be quite profound. So does this mean we might be able to someday traverse a real wormhole in space-time to travel instantly from one faraway place to another? Well, keep in mind that this is a quantum mechanical simulation of a wormhole and not a real wormhole in space-time. They're just mathematically equivalent. Most scientists are skeptical about how far we can push this analogy between entanglement in quantum particles and real wormholes created in space-time. Real wormholes today are still a fantasy. What's my overall opinion? I think this experiment is not as irrelevant as some scientists are saying. This is still a great step forward because it appears to confirm some conjectures that attempt to combine quantum physics with general relativity, showing that a unification may be possible and that these are not such crazy ideas. And this is the kind of thinking and experimentation we probably need to make progress towards a quantum theory of gravity. I think it's good that people have crazy ideas because sometimes they're right. Einstein was considered crazy. Einstein thought quantum mechanics was crazy. I can't think of a single great paradigm-shifting idea that was not considered crazy when first proposed. So let's be skeptical, but also open-minded.